TUBS-IRMB. Digital India. Educated India.
So, welcome to this tutorial in this GIAN course in high fidelity lattice Boltzmann method. And these last two tutorials that we are talking here is a little bit of a different kind than the previous tutorials. Here we talk about the open source lattice Boltzmann VirtualFluids, which is a solver that we develop at the IRMB in our lab. And I have a few things to say up front. So first thing is that there are now many open source lattice Boltzmann solvers, and they may be more or less versatile than ours. The thing is, other groups actually earn money with their open source codes. It always sounds like your open source does not mean you're earning money, but you can sell like consulting or something. We do not earn anything with this code, and I'm also not a salesperson. I don't want to convince you to use this code. So we are offering this code. It's also due to the policy in Germany that we have to offer our code in order to be scientifically open, to publish reproducible results. We have to be open source. Yeah. We also like if the code is useful for others, but it is not our primary purpose to sell something. And I'm also not trying to convince you about anything here. So this is the one thing that I have to say up front. And the other thing that I have to say up front is that while I'm developing this code, I'm not one of its main users. So usually I have people working in my lab that write all the setup files. So I hope I'm not talking complete nonsense. And if later I don't know what this particular variable means, this doesn't mean that I'm making something up. It's just that 99% of this code is written by somebody else. I'm responsible for the theory behind it, and people are programming it and using it. So okay, VirtualFluids. This is its name. I think probably I've seen these things here before. So because again, we are not selling something. We also don't try to include everything in the code to make it, this versatile thing where you can select this MRT and this BGK and so on and so on. So basically, we focus on the things we believe are important. And the things that we believe are important is, of course, the cumulant method that we have been talking about today. So we are using cumulant, we are using D3Q27 lattice. So again, we are not offering many different collision kernels. We are not offering many different lattice discretizations. We focus on the one thing that we think is the most important. The code actually comes in two variants. One is for the CPU, and this is also one that we are going to discuss a little bit today, and the other one is for the GPU. We always want to get them closer and closer together, but they use kind of little different data structures, and therefore they still need to be separate. Okay, so then there are a few specific algorithms in it. One of them we will discuss on Friday. This is the Chimera transform. The Chimera transform is a quick method to compute central moments, and from the central moments you can then compute relatively easily the cumulants. As some of you have experienced yesterday, computing central moments itself is a little bit tedious, in particular if you want to track this back to getting the populations from the central moments. So there is actually a fast way of doing this, and this is called the Chimera transform, and we talk about this on Friday. Then there's also faster and more efficient ways to store and access data. So in the algorithm, in the example algorithm that we had the combination of streaming and collision, right? But we needed two populations, one before collision and one after collision. Then there are some algorithms. One of this is this esoteric twist algorithm that combines streaming and collision and use only one population. Yeah? And do this in particular in a thread-safe way. In a thread-safe way means that we can access this in arbitrary order. This is important because we use, of course, parallel computation. The GPU uses usually thousands of threads, and also the CPU code can use thousands of threads if you are on a big enough machine. So usually if I do it in my laptop, I will use 4 threads, and if I do it on my desktop, I will use 24 or so threads. But if you're on a very big machine, you can use thousands of threads because it is implemented actually for high performance computers. Then there is one change I'm going to explain a little bit later, and because I'm not prepared, I don't actually know in which order that my slides come up now. But I decided I talk about this a little bit later. One change with the cumulant method that is relatively complicated, so we could not talk about this in the lecture today, and we have only 2 more lectures. Okay, so examples that has been done with this method have been, for example, we do city scale simulations. So this is a part of Basel here, where we're interested in actually fine dusts. Yeah, so this we will then do with Braunschweig, fine dust distributions coming from especially brakes and tires. And so we'll also have simulation of the traffic. Here, this simulation was just the air. Yeah. So I discovered yesterday, because we had the rain here, Braunschweig had twice the fine dust pollution than Chennai. I think this is usually not the case, but yeah, so we have we actually have better air today than we have in Braunschweig. So Braunschweig, of course, also is not complying with the WHO recommendations of air quality. Yeah, as almost all places, all cities on Earth nowadays, unfortunately. We had this. I've also shown this. We have done acoustic simulations, which I cannot, due to the way this is recorded, I cannot show this now, but you can actually make this organ pipe, you can generate this tone, and then we are doing a lot of stuff with porous media and turbulent flows. Okay, so one thing that I also want to highlight is that if you want to install VirtualFluids, there are a few dependencies, not too many, but you need MPI, you need CMake, and you need Git. So these are the minimum requirements. And you need to understand and correct our mainly, maybe not completely correct installation guide. Yeah, so you have it a little bit simpler if you use Docker images. Yeah, so we provide Docker images where everything is already installed in this. This is also important if we publish particular setups for a particular paper. Yeah, so I mean we are required now by by law, actually, more or less, that when we publish simulation data, we have to make it reproducible. I don't know how this is in India, but if it's not, then it will come. Yeah. So to have reproducible results, you have to give your code away together with this. And with self-written software, this may be complicated because this is designed for a specific, especially high performance computing. Yeah, this may be designed for a specific setup and computer and a specific system. Now you can encapsulate your system into a Docker file, and then the hope is that in principle, 20 years from now, this can still be executed. That's the hope. We don't know. Let's see. Okay, so for example, this Docker image here that was in that particular paper, you can download and reconstruct whether you can reproduce this gravity flows that we have been simulating with it. So now coming to a little bit of theory included here, because we could not go to this in the lecture. And this is based on the asymptotic analysis. Yeah? So there's a reason why this is very important for us here. So this is what you have learned. This is the Lattice-Boltzmann equation. This is the Taylor expansion. And then there's a moment transform. And then I guess on the next page, we also have the asymptotic expansion. We have diffusive scaling. And then we get the continuity equation and the Navier-Stokes equation. Yeah? So, and this tells you that Lattice-Boltzmann solves the Navier-Stokes equation, and then you say, so what? We've known this anyway. Yeah, this is written in this book by Tim Krüger. Okay, should be the case. But what we can do now, and what we have done now, is to also derive the partial differential equations for the errors. And this is done. So, okay. Just going back, we get the Navier-Stokes equation at third order in diffusive scaling. What we can do is, because it's a second order accurate scheme, the first order would disappear. And now we can go to the fifth order. And the equation that comes out there is the equation for the leading order error. And it actually can be identified as an inhomogeneous Oseen equation. So this is the type of equation. What it is, an Oseen equation is like a Navier-Stokes equation that is driven by an external velocity. Yeah? And if to an Oseen equation you set zero initial and boundary conditions to zero, so this error term will actually disappear unless it is an inhomogeneous Oseen equation, which means that it has source terms which are related to the solution of the Navier-Stokes equation. Which is the case, and which is the reason why this is only second order accurate. Is there something that we have to, because it's too loud? Okay. So the first time I did this, I don't know whether this is still true. The first time I did this and I printed it out, this equation went over 17 pages. So now you see why I'm why I am a friend of computer algebra systems. Yeah. So I actually needed actually a big computer to do this, and I haven't tried for the last 5 or so years, but since then I was not able to go to epsilon to the power of 7. Yeah. So in principle, so if you want to see the next error, you would go to epsilon to the power of 7, and then you would even see what is going on there. So we have done all of this, and now comes the important part, because this is also related to virtual fluids and our high fidelity things that we have been talking about here. This calculation, of course, is pretty complicated. The result is ugly, and I can only write the, if I want to display it here, I now can write this. Okay, so first of all, this equation is very nonlinear, meaning that there's also problems with Galilean invariance that come from the discretization. And now we have decided to not bother with them, meaning that we actually have second order problems with the Galilean invariance. Yeah, but these are not related to the relaxation rates of our methods. Yeah. So we linearize the inhomogeneous Oseen equation, and we assume that that tau, so the viscosity is small, and then what comes out as a source term for the third order, for this error in velocity, are 5 different terms that depend on the solution of the Navier-Stokes equation. So the first order solution here, all of them come with forced derivative. And they all depend on 3 different relaxation rates, which are all related to the third order moments. You remember we have 3 different third order cumulants, yeah? And they 3 different types, or we could identify 3 different types to which we attach 3 different relaxation rates. So, and of course, one of the open questions is how do we set them? And so if you don't have any idea, yeah, you set the relaxation rates maybe to 1, yeah? So remember, tau is not the relaxation rate. Tau is 1 over relaxation rate minus 1/2, yeah, because this looks a little bit simpler. Okay, now these are these functions g here. Now the question is, could you somehow eliminate these terms with a specific set of relaxation rates? This is a difficult question because in addition to whether these things would disappear, the relaxation rates would also be in the stable frame between 0 and 2. Otherwise, this wouldn't work. And actually, the result that comes out is not always in this regime. Yeah, that's also important to notice. But another problem that you see here is that this is never going to work because we have only three of these rates, while we have 5 independent terms. So there would be a coincidence, a very, very rare coincidence that this would disappear. So fortunately, so the reason why we did this analysis in the first place was that after many years thinking about this problem, I decided to prove that this is impossible to solve. Yeah, and now in order to convince my PhD student that it's actually impossible to solve, I had to, write down all these equations, and then I had these equations in front of me and looked at them harder, and I said, okay, it obviously cannot work because I have too few degrees of freedom, but I can manipulate this equilibrium functions of these first order cumulants somewhat. So now I told you that their equilibrium is supposed to be 0. Yeah, but I decided so I can squeeze a parameter into this so that they are not 0. This makes the entire thing anisotropic. Yeah. However, there is an anisotropy coming from the lattice. So basically, the idea is we combine 2 anisotropies in order to eliminate them together. So squeezing in these 2 parameters now gives us 5 parameters with 5 equations. And the funny thing is that there is actually a solution. And the solution the solution looks like this. And I cannot explain why it looks like this. It's not horribly complicated. But the thing now is, I have to explain. This tau is the one for viscosity. Tau 2 is what we had with omega p. Omega p is the one for the bulk viscosity, the attenuation of sound waves. Yeah? So these two things we consider to be physically given quantities, physical quantities. Yeah? So then we have free relaxation rates of the third order moments. Only third order moments show up. We still don't know how to set the fourth order moments, because then we have to do the asymptotic expansion to the seventh order in order to see this, but we are only able to do it to the fifth order, because asymptotic analysis, I don't know whether you noticed this, but if you increase by order, the length of the equations increase exponentially with the order. So going 2 orders higher is not as easy as it sounds. Okay. So we only have this third order relaxation rates, which you find all have to be put to different values. All of them have to be put to a different value in order for them to actually work. And there is another constraint which I cannot currently identify. Okay, so there's another constraint here that is, yes. So, okay, you see another constraint down here. And this is basically maybe the reason why it was so difficult to find the solution in the first place, because there were people who tried this before, but they always, because of the complexity of this problem, they always made assumptions up front. And one of the assumptions that they made up front is that tau 2 equals to tau. And if tau 2 equals to tau, this here will be infinity. So we can do this, but we have to use a different bulk viscosity than the shear viscosity. Otherwise it doesn't work. And we also have to assume that the viscosity to the cube is 0. Otherwise we don't get the solution. But this now works because we are dealing with small viscosities. Viscosity to the cube is 0. This is not a big deal. And this is where the thing is published. So what does this mean? We remove the inhomogeneity, at least for the one that is related to viscosity. We remove this from the Ullseen equation. This means we have no source term anymore in the error equation of this cumulant method, and therefore we increase the convergence of the cumulant methods, which we then call super conversion. Now you can do very, very simple measurements, like a crossing shear wave example, and measure what is the error. So I just go through a few of them. Yes. So the cumulant method is the one down here. So you have so these are different viscosities. And we have an error that we measure in viscosity, and here we increase the resolution, so the error is obviously going down. You could say disappointingly, it's not necessarily going down with forced order, because we still have an error in viscosity left. So I may be mistaken saying that this is really forced order, even though if you make the viscosity smaller, it looks like forced order for a longer time, actually up to a pretty high resolution, and up to a pretty high accuracy. It could look like forced order accurate, but it's technically, it's not completely forced order. But even if it's not forced order, you see that the error may be orders of magnitude smaller than if you don't do this. And also orders of magnitude smaller compared to, for example, BGK. And this can be seen also for Taylor-Green vortices. And here basically, the idea is, I don't know why this came out like this, but if you look at this convergence, now what this thing means, even if it's not necessarily higher order, but if you have 2 orders of magnitude in error less, yeah, then this means that if at the same, I mean, if you want to have the same error, like this blue one is now the cascaded one. So cascaded is central moments. Yeah, central moments, cumulant is cumulant, and then there's this. So there's the cumulant without optimization, cumulant with optimization. Yeah, and you see errors are at high enough resolutions. Errors can be 2 orders of magnitudes, yeah, smaller than in the original in VGK and all the other methods. And the way you can now evaluate this is probably not easy here always to see, but you would have to decide on an error that you find acceptable, yeah. And so, for example, if you find this error here acceptable, then you would have to have this type of resolution, yeah, which I cannot read now. So this is 100. This is okay. There are too few steps on this, unfortunately, yeah. But so if you find this error acceptable, then you would have the same error with the other methods at a significant lower resolution, meaning you spend much less effort. And one way to see this, and I've shown this in Monday last week, is that with this method, we were actually first able to use on a Cartesian grid. On a Cartesian grid, we can resolve the track crisis. Yeah. So basically, if you could say that we can do this with OpenForm too, but OpenForm uses a body fitting mesh, yeah, with extended elements. Yeah. So what we need as a resolution is we need to resolve the sphere by 500 grid nodes, but then we're using Cartesian grids and we make it coarser outside. So tomorrow we'll talk about grid refinement, how we do the grid refinement. But we need a resolution of 500 points here. And if we do this, we can actually capture the transition here. So the transition of the boundary layer with this cumulant methods, not using any turbulence model at all, right? So I mean, turbulence model, yeah, slip velocity, you can do this. You can do this with body fitting boundary layer meshes, but this is now done with a Cartesian, on a Cartesian grid, not using any turbulence model, just using super convergent lattice Boltzmann methods. Yeah, and if you do this, so this you cannot do at a similar resolution with either BGK, with MRT, or with cumulants without this optimization. Okay, I guess that's basically. So this here is just showing the pressure. Talking about the VirtualFluids itself. So VirtualFluids can be downloaded from the web page of our institute, the GIAN. There you can go to VirtualFluids repository, yeah, and here you can download the codes. Hopefully it's sometimes updated. Now I'm not going through the installation details. This is described here and probably, so I think it's doable, but it requires you to have some understanding of Git and other things. So, you know, there's so to say an entrance resistance, yeah? So you need to understand something about codes in order to get it actually running. And then we come up, potentially to an example. So I have to explain. So VirtualFluids is not your favorite software coming with an user interface. So what is actually a library. And for this library, if you want to run a simulation, you have to write an application file. Yeah, so you write an app for your particular problem. And then the library can use two solvers, but the solvers I interacted with in different ways. So you have the CPU solver, which we'll talk about today, and you have a GPU solver, which has different data structures and therefore has to be dealt with in a different way. Now, there are Python bindings such that you can run this from Python, but this nobody I know of actually uses them. Everybody uses the C++ version itself and just do the programming in the C++ version. So, and with the distribution, with the software comes a few apps like laminar pipe flow, laminar plane flow, and the one that scientists don't like but are always taught, the first is lid-driven cavity flow. Now this is now a three-dimensional lid-driven cavity flow, and these files usually look like this. So you have to include obviously VirtualFluids and everything else that you are going to use, because this is completely usual C++ code. Now you need a main function, yeah, that is actually running your simulation. And now in principle, now you could do here anything, but what is usually done is we are of course using some of our infrastructure. So we're using lockers, and we're using a configuration file. So you don't need to use a configuration file. You can put everything in the code and then compile it all the time. If you use a configuration file like is provided here, then, for example, your configuration file may look like this. So these are the comments. And then you specify some variables. Yeah? Like, for example, in this case, the path, the length of your domain, the Reynolds number, the velocity. Now, these are physical values, obviously. The time step, and nx would now be the number of grid spacing in one direction. And here, the time step out and time step in. But you can define these things yourself. Yeah? So these are not generic variables of VirtualFluids. Instead, they are things that you can read, yeah, from with our file reader here. Yeah? Now you can specify whatever you want, like for example a variable path, and this would be put in the string path, and L. Yeah, so this is you read L and put this into the real. Yeah, we use this type def real in order to work with floating point numbers. So at compile time in the CMake, you can decide whether you want to have the thing compiled in double precision or in single precision. Yeah, so this cannot be changed now here, but this is when you compile the entire library, you can decide whether you want to run it, with what precision you run it, and then real becomes either single, double, or whatever you decide. So now here you can specify your things and read them from the configuration files. In the cases that you see in the examples, they are usually similar. So you have a time step out, time step end. And here you also get a number of threads. So originally, if you download this, the number of threads is put to 1. Yeah? These are the OpenMP threads. So I think we have seen there are possibilities, for example, on Mac, that there was not an intrinsic, that OpenMP is not intrinsically available. So you have to make some changes potentially, and in order to use OpenMP, but you can also use it without OpenMP, then you have only one thread. And this OpenMP, of course, is shared memory parallelization, yeah, which is not suitable for high performance computing usually. Therefore, we use OpenMP and MPI altogether. So you always need MPI. MPI is always running and together with this. But here you get the OpenMP threads. So this is OpenMP. Obviously, is useful if you run it on your desktop or your laptop. Yeah, then you will always use OpenMP. But if you go to a cluster, then you would obviously use MPI, or you would actually use a combination of MPI and OpenMP, because your cluster node would have so and so many cores. So you would put so it will have 20 cores said. You would use 20 OpenMP threads, and then the rest in MPI. Okay, so here there's a determination of a delta X, which is the grid spacing, and then we have to do the translation between the world coordinates and the lattice Boltzmann coordinates. So, for example, you have this velocity, and you multiply this by dt and divide by delta X, and then you get the velocities in lattice Boltzmann unit, for example. Yeah. So then we come to the setup of the grid, and what we are doing today is we are looking at a relatively simple example where we just use a Cartesian grid and only a box grid. Yeah. So, but whether we use a box grid or anything else, in order for the grid generator actually to generate an appropriate grid, is we need a bounding box in which our simulation lives. And in this case, because the lid-driven cavity is a box, the bounding box comes almost, the bounding box comes at the same size as the simulation domain itself. So we specify to go from minus 0.5 to 0.5. And these are, of course, now world coordinates. Yeah? World coordinates. And the nx that we read from the input file is the number of nodes that we put here. And L was the length. Yeah? Actually, I just noticed that this is the way this is programmed is actually not optimal, because L is read from the read from the input file, and the bounding box is given here as fixed numbers. So okay, you can debate whether this is the right way of programming things. Actually, this should be dependent on L, but it is not. Okay, now here the next thing is that we need to get the communicator. So we are using MPI. So you're familiar with MPI, yeah? MPI needs a communicator, and also needs to know what process they are. So later on, we'll often ask my ID and only do the output when the ID is 0, so only when we are the root process. So then we have to generate, unfortunately, I have to look these things up myself all the time. So we have to generate a crit, yeah. We are using, so what are we doing? We are using here smart pointers, yeah. So smart pointers for all the different things that we generate. So we generate a smart pointer on a crit on the 3-dimensional crit 3D. We generate a new crit, and this also takes the communicator for the MPI communicator, because this crit will then be distributed over different processes. For this crit, we have to specify what is our delta x, so set delta x, obviously, with delta x. And then comes the block size. So our two versions of VirtualFluids, because they use different hardware, they also use different data structure. And the CPU version uses a block-based data structure, while the GPU version uses a list-based data structure. Now, this block-based data structure requires the definition of the size of these blocks. So in VirtualFluids, the blocks are all of the same size. There are other open source Lattice Boltzmann solvers that have, flexible block sizes, but here we go for homogeneous block size. And in this particular case, we set the block size to a cube. Yeah. And this is then also written out into parse plus geo crit cube. So because I've already run it, I can show this. I also loaded it already. Yes, I already loaded it. So you can. It will generate whatever you specify, but the way all the examples are set up are usually like this. That we write out a folder where you get the boundary conditions, where we see the blocks and where we see the geometry, yeah, and then where we see actually the simulation results. They come in these files. So in this case, I've already loaded it here, yeah. So you see, we make the block size 1/2 the number of the grid spacings that we have in our cube. This means we'll generate 8 cubes. Yeah. And by the way, each cube then is treated by its own thread. So if you have more processors, then you would potentially like to set the size of this grid smaller. Now my laptop has only four cores, so then actually having eight blocks is a good choice, because there is no point to have more threads than you have blocks. Yeah. Each block will then be dealt with by one OpenMP thread. No, the OpenMP. So yes, okay, there's a good point, but I mean, so with OpenMP are associated to a set of blocks anyway. I mean MPI. MPI has their different blocks. So OpenMP2 is that it is divided over the blocks. So you see me struggling because I did not program this part. I'm dealing with the equations and not so much with the code. But if I think back to the code that there is no pragma, I believe, in the kernel, so it's actually it's actually one block, one thread also for OpenMP. This is at least what I believe. Okay. Right. So then we create our grid, and here we decide to create a grid that is in form of a tetraeder. Unfortunately, you see there's another thing that is probably not optimal, because this is called grid cube. But this grid cube doesn't mean it is a cube. It means that the entire domain is discretized as a tetraeder also, because we have here different sizes in different directions. Now in that particular case, it will of course be a cube, because these values of G min x and G max x, they are all the same, because we have a cube. So, and then we write out our grids. Write object, we write out our grid, and then we also do our logging. So these are a few things that will be written into the log file. What is the velocity and so on. So you can decide on these things yourself. Then, so then there comes, of course, a lot of infrastructure that you have to do. We have to, okay, so the entire thing is programmed using design rules, the usual design rules, where you have visitors and factories, and this is what we see here a lot is visitors. So visitors is external functions that are kind of interacting with a certain object. I'm hoping I'm not saying complete nonsense here. So what we usually do, I mean, we will later see this in the simulation, that may make more sense. So we have these objects and we want to do something with the object. So we define a visitor, and then we let the grid here accept this visitor. This means during the simulation, the function of this visitor will be then executed on this grid. This is more flexible than to put everything into the grid itself. So we have the functionality external, and we can attach this to the object on which it will work. So then we have to also generate a lattice Boltzmann kernel, and for this there are different possibilities, and this K70 compressible Navier-Stokes kernel is the one that I've described here, and the reason why it is called K17 is because it has been published in 2017, and K is basically the indication that it uses cumulants. So in many European languages, cumulants are actually written with K, and C was already taken for central moments. So cumulants methods are usually indicated by K. This was not my idea. Somebody else did this first. Yes, so this K17, and this is compressible, so there's also an incompressible version, and there's a Navier-Stokes solver. Then we have to produce boundary conditions, and for boundary conditions there are again several options. So we have to do several things here. We first have to generate a boundary condition object, and then we have to attach this to the certain places where this is used. So reason is, of course, that you could have, even for example, no-slip boundary conditions, there could be different solutions for this. So for example, a simple bounce back, or you can have an interpolated bounce back. Yeah. So for example, we generate a pointer for this. We generate such an object, yeah, a no-slip object, and then we decide on the algorithm. So the strategy is the algorithm that we're using, and the algorithm that we select from the ones that we have implemented here is the no-slip interpolated one. That is the single point interpolated boundary condition that we had in the end of the lecture of the on the boundary conditions. Then something else that we offer, and this is now significant for the velocity boundary condition here, even though this is pretty simple, is an expression parser. Now, in a way, this is now boring because our expression is here just u. But suppose you have something more complicated. A simple example is you have a certain inflow profile. Yeah. Here now our inflow profile is constant. Yeah, but we can demonstrate this so. So there is something that is called a mu parser. This is an external thing that we're using here. And we generate a function, and here in this we give this function that is then this expression that we're using for the boundary condition. Yeah. So now this is u. This could also be u square root of u as a function of the coordinates or whatever. Yeah. Usually it's u as a function of the coordinates. Can also be a function of the time. Yeah, so we set let me see. Okay, we set the expression to u, and then we have to define our variable. So in this case, we have only one variable, and we just want to set this variable. Yeah, so the variable u is set to u. For more variables, we have to set more things. Yeah, and then this is now supposed to become. So we have a cubic lid, and what we want to do is we want to have this in both directions. So one way of implementing this is so there are different velocity boundary conditions. Yeah. So in this case, actually I don't like this one, but in this case. It just gives a scalar input. Yeah, we also have a version where you give a vector input. Yeah, so here gives a scalar input, and we set this to the x and the y and not to the z value. Yeah, I potentially like the one with the vector more because it's more intuitive. But this is the way it is here, and so. Then this boundary condition takes place from time 0 to time infinity. So there's other things that we have to specify here. Okay, I mean the thing is recorded. I know this is now a lot of detail. I just want to show the different parts. Yeah. Then for this boundary, we also have to have a strategy, which is the algorithm, and this is velocity interpolated. So we also have an interpolated velocity boundary condition here, which is potentially not necessary that we do it interpolated because we are on a cube and have straight walls. Okay, then we also have to put this is also designed as visitors, and we have to add these things as visitors to the grid. So we first have to define the visitor, and later we have to accept this visitor. Then comes here some more detail, that we use a certain way to apply the boundary conditions. Now this is related to the fact that we may have boundary conditions that can access the node, or we have flat boundary. So the reason why we have this is because sometimes we cannot put the boundary conditions directly on a node, but we have to put them somewhere in the middle of the domain, which we call a thin boundary. For example, you have a thin wall that actually covers no points. Yeah? So this has to be treated in a different way. Therefore, because we have this possibility, we now also have to tell them, so here we are dealing with the usual boundary conditions, and this is why we have to produce the data structure for the boundary conditions individually, and cannot just say, so do the default. Maybe this can also be improved. Now, what comes here is that we set the geometry of these different boundary conditions. So this is something that again we can see here if we go to geometry. Yeah. So we'll write out these different. Let me see whether I can actually read all of this. So we have the different walls, and we have the moving wall. Let me see whether I can open this in one go, whether I can then accept all of them. Right. So you see we have here these. Maybe I should have them in wireframe. You see you have to put objects. I cannot do all of them together, I guess. Wireframe, 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 wireframe. So so we have these different boundary conditions all around, and where they touch, so they need to have a little overlap with the grid, and where they overlap with the grid, the boundary will be generated, and automatically by the grid generation, the subgrid distance will be identified such that the interpolation can also take place. Yeah, so they are put now here all around, and you have to obviously you have to generate them for all the 6 different directions, and we also write them out. And here we have to add, so we generate these things, then we add the boundary condition that we have. So we have generated this no-slip boundary condition. We have added to this a certain algorithm, and now we add this to this particular walls. Yeah, we have a different boundary condition for the velocity boundary, and then we have to add this to the grid. Yeah, and we have to select blocks. This is one of the things that I cannot explain. You know what exactly this is. I have to ask my colleague. Yeah, and then we. So here there's some writing out, which you only do when you are the master process, the root process, and then we do the grid generation. So the grid has to accept the different visitors. We have to set the boundary conditions, and then we also have a visitor pattern for the initialization, which is also set into the grid. And then we have the BC, the boundary conditions that are set to the grid. And then what we do here is writing out some data files, doing some logging. And then we also add simulation observers. So in simulation observers, again, is something that is some algorithms that run during the simulation. For example, you may want to have a performance measure during your simulation. Then you will have this is this one here, creates coprocessors. Yeah, so you have an TUBS scheduler, TUBS simulation observer. Yeah, this is actually an observer pattern. So you add these observers to the simulation, and then they will be executed during the simulation. Could also be an average, something that's averaging things, and of course it is the writing out of the files. Then we set for the OpenMP, we set the number of threads, obviously. Yeah, and then we create our simulation. To the simulation, we add the observers. In this case, the observer that we have is the performance observer, and this MQ observer is this, I believe, where did we generate this update? This is get instant velocity. So this is the this is, if I'm not completely mistaken, this is the writing out after so and so many time steps, which we basically specify in the input file here. So I've set this time out to 1,000 and end time to 10,000. Okay, now I'm in the wrong file. Then we do some logging and yeah, run the simulation run. Yeah, there's also the option that we do a rerun, so that we write out you know, the old state and recover this and run from this again. Okay. I hope some of you are still listening. I know this may now not be the most you know, if as long as you're not using this may not be the most interesting thing. It's being recorded. Yeah, I wanted to give you some overview. Okay, now we can run the simulation. Unfortunately, if I run the simulation, I overwrite what I had here before. This is, I should close this. This is irritating me because this is not what we are using. So, for example, we can have a look when the default was here to set this to one thread. Okay, I run the simulation from here. We can also run this from the, we can obviously also run this from the command line. Then you will have to give the name of the input file as your command parameters. Now you see how much physical memory is available or is used. I don't know memory currently used. Okay, so this is the memory used. I have apparently 34 gigabytes. This is the amount that is used. We are not running with one thread. We have a performance of 2.9 million node updates per second here. And each 100 time steps take about 9 to 10 seconds. Yeah, so this may not be what we want if we increase the numbers of threads. So this is a laptop. It's already pretty old, so it has 4 cores. I guess I let it run with 4 cores, and now we have the problem that this Zoom works with it, and we actually want to have the recording. So what I'm going to do is I'm just starting it and see what happens, and then I let it be, yeah, because I don't want to ruin the recording, and they are I mean, this obviously makes my computer rather hot. So we see Zoom is working in the background. We had some 10 seconds per 100 time steps. And now we have some 4 here. Okay, don't want to ruin this. Now my problem is that I've potentially overwritten my at least one of these files. Previously I run it to a time step 10,000. Let me see whether it still has this in memory. Yeah. So don't reload anything now. We still have them in memory, but only the first 10,000 time steps, of course. Yes. Now I don't know whether you are familiar with ParaView. So this is also used by OpenForm, for example, or you use it together with OpenForm. So you write out your data here. This will come up like this, and what we usually write out is the density and the 3 components of velocity. So the velocities is here not written out as a vector. If you want to have it as a vector, you can use the, for example, the calculator here and generate a vector. This, unfortunately, you have to do by hand, but it's not so complicated. Like, you build this vector from the scalars plus, what is this, v set times k hat, and you could call this, I usually call this velo, yeah? So then you have the vector valued, and with this, for example, you could the filter and use, what are they called? Streamlines. Are they called streamlines? As slice, streamlines. For example, we put them on the calculator, and no, this was a streak line. I didn't want a streak line. I didn't want a streak line, I wanted to have a streamline. Streamline, why do we have? That is not optimal. Okay. I usually don't use this computer. I don't for simulating. Yeah, I don't know what problem it now has. Difference, mesh, velo, mesh time, wait. There's again streak line. Okay, I'm making a mess here. Filter alphabetically says streak slice, stream tracer. Okay, stream tracer. Okay. Okay, maybe I mean something else. So stream tracer. So what you could, for example, do with the stream tracer is taking the Boltzmann integration line. Maybe we do a point cloud. Yeah. Okay. Don't know what I did there before. So because we did not run it for a very long time, so this tracing here may look not so very interesting. We can, of course, now put, okay, so it calculated rotation and vorticity. Why did this do this? Okay, I don't know. So here you can display some velocities. Yes. When you load, by the way, when you load the data, so the data comes into this place. I've already loaded it, and I don't want to reload it because then it's empty because we rerun the simulation and we terminated it. But you should read this collection. Yeah. So when you open this collection, you actually get here the different time steps that you can go through. Okay. Do you have any questions about virtual fluids? Yes, what is a visitor? I would rather let my co-workers explain this. You know, this is why I didn't like to give this presentation. A visitor is one of the design patterns. So there's observer, and there's the visitor pattern. Yeah, because now I'm completely making a mess. So is a behavioral design pattern that lets you separate algorithms from objects which they operate on. Yeah, okay. This is also true for an observer. So an observer is something that you attach to something, for example, to the simulation, that during the simulation will get some information out. Yeah. So the visitor is, I think, is somewhat more general. Yeah, so basically you have better you read it in the book, but I try to give my amateurish explanation to this. Yeah, so you have your object, like where you have your data in it, and on this data something has to happen. And now you, instead of attaching the algorithm within this object, you have an external object that does this algorithm, and then you attach this to the data as a visitor to the other object. Yeah. So this is like an agent that comes to your object and does something with that object. Yeah. So here is probably this explanation here is probably much better than anything I can explain. But maybe, so yes, I encourage you to go to the library and read about design patterns, or actually you can go to Refactoring Guru or something like this, where they explain all of this. You can also just type into your favorite artificial intelligence tool, give me an explanation. So for example, we can use this, we can potentially use this here and just say explain the difference between the visitor and observer design pattern. So unfortunately, artificial intelligence can in this maybe better in explaining this than me. Purpose: the visitor pattern is used to separate an algorithm from the object on which it operates. So okay, this is what I said before. It allows adding new operations to existing object structures without modifying these structures. Yeah. So how does this is different from the observer pattern? Is used to define a one-to-many dependencies between objects, so that when one object changes the state, all the dependents are notified and updated automatically. Okay. Yes, I think what I said was not completely wrong, but I'm not the best guy to teach these things. So design patterns. So the entire virtual fluids is built up on these design patterns. I think we also have this in our paper. So the advantage of using design patterns is, of course, that other programmers that are familiar with design patterns, obviously, yeah, immediately get an idea what this thing is actually doing, because it's also called visitor, yeah, visitor or observer. So when they read, when you are familiar with design patterns and you read this is an observer, then you know now this uses the observer pattern and this uses the visitor pattern. So it becomes easier for other people to actually understand this. This is the hope, and we discussed this. Built-in testing, design patterns. Okay. Or maybe we don't discuss this here. Okay, so what paper I'm showing here is a paper that is not officially published, but which you can find. So VirtualFluids open source parallel LBM solver is still under review, but you will find this paper on the web page, or you will find this paper anyway in the library of the TU Braunschweig. Unfortunately, when I try to do this from here, I get too many withdrawals. So apparently this web page is somehow blocked from India. Not because we don't want. I mean, this is a university page, so we don't care about you having it or having it. I mean, you're welcome to have it. It's just that apparently there is some problem with the access of the university library from here, saying that apparently they try to avoid some automatic, attack. Yeah. So like I don't know why this is my IP address. It must be an IP address that is somehow related to India, because I'm now coming from India. I don't know. You can look it up yourself. Maybe it's actually the fault of this computer over eduroam. I don't know, but I cannot access it from here. Yeah, I have to download it from my other computer. So, VirtualFluids open source parallel LBM solver. In this, we actually describe the software. So anybody can try to. I don't actually know where to. You probably it's probably not found by Google, because it's the local server. Yeah, because it's not yet published. Okay, you're looking up for, you can wait for this paper, VirtualFluids open source parallel Lattice Boltzmann solver. If you type this in, you will end up potentially at OpenLB, because the first thing you find, you can add TU Braunschweig. Maybe this, are there any further questions? So some of you have already downloaded it and seen that it's possible to use it. They also recognize that it's not necessarily that simple to download and install it. So the suggestion from my colleagues is always, if you don't want to spend too much work in the installation, use the Docker file. Yeah, there the system is already set up, but of course you need to have a Docker installed. Okay, so if there's no further questions, then I would say it's 12 o'clock almost. Tomorrow we have a lecture on grid refinement. And then in the afternoon, we'll also look at an example that VirtualFluids, not in the afternoon, no, after the lecture, we'll also see that VirtualFluids can actually be used together with grid refinement. Okay.